Welcome to Phantastic Physics. Today I have a very interesting question for you. Imagine we lived on an Earth where instead of being its normal size, we doubled the radius of that planet. So if Earth suddenly became twice the distance from the center to the surface, and we went from a small Earth to a much larger one, by doubling that radius, what would happen to the force of gravity felt by the people living on this planet? So would they feel more gravity, less gravity, or the exact same gravity on this type of planet versus regular Earth? And I'm going to throw one more piece of information in. Let's say that when we double the Earth's radius, that we don't change the Earth's mass at all. So the current mass of the Earth is the same as the new Earth. It's just much less dense because that mass is being spread out over a larger size planet. So leaving the mass exactly the same and just doubling the radius, would a person on this planet feel either A, more gravity, B, less gravity, or C, the same gravity? And while you think about those three options, I'd like to remind everyone that if you like the concepts in this video, you can access these concepts plus more great physics content by going to the description of this video and clicking the link to the Phantastic Physics store. We offer a full year high school physics curriculum, perfect for teachers, for homeschoolers, for parents who just want to help their kids get up to speed on physics, or for students who want to find a material that is going to help them study. So to answer our question here, we're going to have to look at Isaac Newton's universal law of gravitation. So let me start by writing that on the board here. So it says that Fg is equal to capital G times m1 times m2 divided by d squared. So Isaac Newton said, hey, if you want to calculate the force of gravity, you have to multiply the mass of two objects together. And that could be any mass. So it could be the mass of this eraser and this pen here. And so I could calculate the force of gravity between them by just multiplying their masses together, divided by the distance between them squared. But he also said that there's this missing constant called G, or the universal gravitation constant. So not only would I have to multiply the masses of these two objects together and divide by the distance squared, but I would have to also multiply all of that by this constant G. But the problem is Isaac Newton was never able to figure out what G is. So he actually died before ever figuring out the universal gravitation constant. But luckily, his successor, Henry Cavendish, was able to experimentally find this value of G. And what he found was that G, or the universal gravitation constant, is equal to 6.67 times 10 to the negative 11th power. And it does have some units, but those aren't important for this lesson. You can look them up. So to the negative 11th power, if you know scientific notation, what that means is you take this decimal and you move it 11 places to the left. So if we were to write this number in standard form that most people are more comfortable with, G is equal to 0 point, and then there are 10 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 6, 6, 7. So by moving the decimal 10 places to the left, you end up with 0.0000000000667. So what does that tell us? Well, when I do this multiplication of the two masses of the objects and divide by the distance between them squared, and I multiply by this really tiny number, it's going to really change the result. And that's going to calculate the true force of gravity between any two objects. But it's a really small constant. So what does that tell us about the force of gravity? It tells us that gravity is actually one of the weakest forces in the entire universe. And actually, if you look at the four fundamental forces, the strong nuclear force, the weak nuclear force, the electromagnetic force, and gravity is the weakest of those by far. And it's not even close. And that might be surprising because, you know, we think of gravity as being this really powerful force. I try to leave the planet and I can't go anywhere because gravity's pulling me down. But consider that if you took a balloon and rubbed it against your hair to build up some charge and hold that balloon above your head, that small amount of static electric force is enough to lift your hair strands up. And meanwhile, the entire planet's gravitational pull is trying to pull your hair down. Guess who wins that battle? The tiny amount of charge is able to lift your hair up, while the Earth, its entire higher gravitational pull cannot win that battle at all. So again, gravity is a very weak force, but now that we have G calculated, after Henry Cavendish found this value, we can now calculate the true force of gravity between any two objects in the universe, which is a very, very powerful tool. Okay, so let's go back to our original question. Remember, we were talking about doubling the radius of planet Earth and wanting to know what happens to the force of gravity felt by people living on this planet. And so to answer that question, we are going to use Isaac Newton's universal gravitational equation, but there is something we're going to leave out. Okay, so if you look at this equation, and if I were to ask you how many variables do you see here, what would be the answer? And the answer is 3, right? There's the mass of one of the objects, there's a mass of the other object, there's the distance between those objects, which we're squaring in this equation, and that's it. Those are the only 3 things that we can change in this equation. G is not a variable because the universal gravitational constant is a constant. It's something that can never change. So when we're doing these hypothetical problems where we say, hey, let's double this mass or triple this mass or double this distance or triple the size of something, we don't really need this constant because it's not something that could ever hypothetically change. So I'm going to rewrite this expression and it's going to look a little bit differently. And I'm going to use this symbol now, right? And so if you haven't seen this symbol before, this stands for proportional. And what that means is the force of gravity between any two objects is proportional to the masses of those two objects multiplied together, divided by the distance between them squared. So this is a proportionality expression. It's similar to our universal law of gravitation, but instead of an equal sign, we've replaced that with the proportionality symbol because we don't have that constant G anymore. But follow me and you'll see exactly how I can use this to solve this problem. So let's go back to our situation. What are our two objects? What's our M1 and our M2? Well, we can say that the person living on the planet is M1, so that represents their mass. And we can say that the Earth is M2. That's the mass of the planet. And so what's the distance between you and the planet Earth that you're living on? Well, it turns out that distance is basically the distance from the center of the planet to you. And so basically that's the radius of Earth, right? And so going into my equation, the way to solve this is to do this. For M1, my mass, we're not saying it's changing at all, right? In this problem, in this hypothetical question that I asked you, I didn't say that I was going to increase my mass. So if my mass is staying the same, we're going to plug a 1 in to represent that it's just 1 times what it used to be. It's not changed. And what about the mass of the Earth, M2? Well, remember, if you think back to the beginning of this video, I said in our example, let's leave the Earth's mass the same. Let's not change it. And if we're not changing the mass of the Earth, we're going to plug in a 1 for the Earth's mass. So what's the only thing we actually change in this example? I said that we were doubling the radius of the Earth, which means the distance between me and the center of the planet has doubled. And so for distance, D, I'm going to plug in a 2. But remember, in our proportionality expression for gravity, the distance is squared. So I have to remember to square that distance. And so now I just solve. On top, we have 1 times 1, which is 1. On the bottom, we have 2 squared. 2 squared is 4. And we end up with the final answer of 1 over 4. So what does that mean? Well, that's our answer. It means that on this hypothetical planet that has twice the radius of regular Earth, as long as I don't change my mass and I don't change the planet's mass, I'm going to end up feeling 1/4 of the normal gravity on this planet compared to this planet. So for example, a 200-pound person would only weigh 50 pounds on this planet. There would be 4 times less gravity. And that's pretty shocking. A lot of people I ask this question to assume that if the planet's bigger, there must be more gravity. But wait. When you make a planet larger without changing its mass, all you're doing is moving yourself further and further away from the center of the planet. And the further you get from the center of an object, the weaker the gravity gets, right? And so the beauty of this gravitational expression is I can use it to solve for any problem, right? So for example, what if I doubled the mass of the sun and I doubled the Earth's mass? So what if I double these masses and I doubled the distance between them. So this is another hypothetical problem. So my question is, by doubling the sun's mass and doubling the Earth's mass and moving them twice as far apart, what would happen to the force of gravity between the Earth and the sun? And it's really simple to answer these types of questions once you know how to use this expression, because in this problem, the mass of the sun and the mass of the Earth were doubled. So I'm going to put in a 2 for both of their masses, and the distance was also doubled. So I'll put a 2 for my d down here for distance. On top, we have 2 times 2, which is 4. On the bottom, we have 2 squared, which is also 4. Well, what's 4 divided by 4? Well, we know mathematically that's just 1. So when you run a problem like this and you get an answer of 1, what that tells us is by doubling the mass of the sun, literally, if we did this right now, and we doubled the mass of the Earth right now, and we moved Earth twice as far away from the sun, the gravity that the Earth would feel pulling it towards the sun would not change. It would be exactly the same gravity as the Earth feels right now, which is kind of interesting. And you could run all sorts of hypothetical expressions and figure out, hey, if I move these further or closer, what would happen? If I doubled or tripled this mass, what would happen? And all you have to do, the only trick, is if something is doubled, you put in a 2. If something is reduced by 1/2 or brought closer, you would plug in a 1/2. And if it was tripled, plug in a 3. If it's not changed, just plug in a 1. So a very powerful tool that comes from Isaac Newton's universal law of gravitation. Thank you for watching Phantastic Physics. Please like this video and subscribe to our channel if you want to see more interesting physics content. Goodbye for now, and remember, it's a fantastic universe out there, so stay curious.